Problem 10.59 is an example of a stoichiometry problem that involves gases, where you can use gas volumes when you're not at the same, that the reactants and products are not at the same temperature and pressure. It's a relatively simple problem when the reactants are at the same temperature and pressure. You can use the coefficients to make ratios in terms of liters instead of moles. And we're able to do that, we can understand that because of Avogadro's law that says for any gas at the same temperature and pressure that the volumes and number of moles are proportional. Now it's a little more complicated when the reactants or products or when the reaction components are not at the same temperature and pressure. And so I wanted to take a look at how you would go about solving that. So in 10.59 it says that we are to react methane, which is CH4, completely with oxygen. Now this is a combustion reaction of a hydrocarbon. So in the complete reaction we would make carbon dioxide and water. Now you need to balance this equation because when you're doing stoichiometry problems you need the the coefficients for the ratios in the stoichiometry problem. Now in this problem, if I'm rereading it, it's asking me how many milliliters of oxygen. So I need to figure out how many milliliters of oxygen. And I've measured the oxygen at 27 degrees Celsius and 654 torr. Now they tell me that I have started with 16.8 milliliters of methane, and I am at a temperature of 35 degrees Celsius and 725 torr. Okay, so this is what I mean when you look here, the two reaction components, this time I was given two reactants, are not at the same temperature and pressure. So I simply cannot just use their 2-to-1 ratio. See, here's a 2 and here's a 1. When there's no coefficient, it's 1. So I know the ratio is 2-to-1, but when they're not at the same temperature and pressure, I can't simply use the ratio. So there's two ways to solve this problem. The first way is to use the combined gas law. And so the combined gas law is P1V1 over T1 equals P2V2 over T2. Now what I'll do is I'll take my methane, the current conditions, and I will calculate the volume of that methane at the same conditions that the oxygen is at. So I really would be solving for V2. So if I rearrange the ideal gas law, V2 would equal T2 over P2 times P1V1 over T1. Okay, so now let's plug in, but before I do, I want to remind you that the temperatures must be in Kelvin. So temperature 2, this is going to be temperature 2, and this is pressure 2, and this is going to be temperature 1, and this is pressure 1. Now remember, what I'm trying to do is convert, change the temperature of my methane and the pressure of my methane and determine the volume of my methane. So I'm actually not determining anything for oxygen right now. This is all for methane. So 27 degrees Celsius is going to be 300 Kelvin. Add 273. And this is 655 torr. I don't have to convert pressure. And then I'm going to multiply it by 725 torr. times volume 1, which is 16.8 milliliters. And I'm going to divide that by 35 degrees Celsius, which is 308 Kelvin. Now, when I solve the math for this problem, I get that the volume of my methane at the new temperature is 18.1 milliliters. Okay, so now now we can solve this like a problem where we have two of the reaction components at the same temperature and pressure. So what I can do is take the 18.1 milliliters. Actually, and you wouldn't have to work in liters, but since the other problems that are in your book, a lot of them have liters, let's work in liters, okay? So I'll convert this to liters, so that's 0.0181 liters of methane at my new temperature and pressure. And since now my oxygen would be at the same temperature and pressure, I can just use the ratio in the volume ratio. So that's 2 liters of oxygen because of the 2 here, the coefficient, for every 1 liter of methane. And that is because of this one here. And so the amount of oxygen that would be required is 36.3 liters of oxygen. So to recap this step, the first thing I did was use the combined gas law to calculate the volume of my methane, at the new temperature and pressure, so that the temperature and pressure of my methane and oxygen could be the same. Once I calculated the new volume of the methane, I then used the ratio, the volume ratio, as given by the balanced chemical equation to determine the liters of oxygen that would be required. Now let's look at the second way to determine this problem. The second way would be to use the ideal gas law. And I don't mind this way. The only thing is you do have to convert more things into more units, because the ideal gas law has very specific units. So we have the same chemical equation that we did before. Both of them, you have to have the chemical equation, because in stoichiometry, in stoichiometry problems, you have to have the coefficients. All right, so working with the same information, this time what you would do first is calculate the number of moles of the methane using the ideal gas law. So the ideal gas law is PV equals nRT. If I rearrange for N, I have that as PV over RT. Now, in order to plug in, the pressure has to be in atmospheres. So if you take 725 torr, 725 torr, and you divide it by 760 torr, because there's 1 atmosphere and 760 torr, you would convert that to atmospheres, because the torr would cancel. Then we'll multiply it by the volume, which has to be in liters, and the volume they gave us originally was 16.8 milliliters. Then you divide by the ideal gas constant, and divide by the temperature, which was 35 degrees Celsius, so it's 308 degrees Kelvin. So now reviewing this problem yourself, you may need to review how you would make sure that you had everything in the correct units. When I solve for this, I get that N is 6.34 times 10 to the negative 4th moles. So this is the number of moles of methane. Now I know if I know the number of moles of methane, I can use the coefficients in the balanced equation to figure out the moles of oxygen. So it's 2 moles of oxygen to 1 mole of methane. And then so this would give me 1.27 times 10 to the third moles of oxygen. Now I needed to know the volume of oxygen, so again I can rearrange the ideal gas law, this time solving using my information from oxygen. So the volume of oxygen would equal nRT over P. The number of moles I just calculated, it's -3. Then I have R. Then temperature, this was this was given as 27 degrees Celsius, so that would be 300 Kelvin. Remember the oxygen, if you go back and look at the problem, the oxygen and the methane had different temperatures, and the oxygen was at 27 degrees Celsius. And then the oxygen had a pressure of, where did I write it down? 654 torr. And you could convert that into atmospheres because by using the ratio 1 atmosphere to equals 760 torr. And when you solve this, you get 36.3 milliliters of oxygen. Actually, I take that back really, because when you solve this, you're in liters. So you would get 0.0363 liters, and then you would say 36.3 milliliters, which is the same answer we got in the previous problem. It's not necessary that you can solve this problem in the same in both ways. I just want you to see that these gas laws are relatively versatile and that there's different ways sometimes to approach the problem and get the same answer.